Hi there, Mel here from Synthesis Health Lab, and in this series I want to do a walkthrough of how our immune system works. It is really helpful to understand the context of how it developed and why it does what it does so that we can make sense of conflicting advice, conflicting evidence, and really understand what we need to do to get well and to take care of ourselves. And it's also just really interesting. So in this video, we're going to go into the evolutionary context of how the immune system works, because really we just need to understand that so that we understand what it's doing and why. So let's take a look. There's a famous quote from a well-known evolutionary biologist that nothing in biology makes sense except in the light of evolution. And this is so true when it comes to the immune system. So in this video, we're going to go into what your immune system really is. It's much more than just defense, how your cells are organized, how the mitochondria orchestrate our immune response. So it's really important to understand what mitochondria are and what they do and how they work, where our mitochondria came from, disease, chronic illness as de-evolution. This is really key. And the mitochondria as a central hub in our physiology. So what is the immune system? Your immune system is a system that is made of cells, tissues, fluid like lymph and blood that's circulating in pathways in your body, barriers like your skin and your gut, and communication networks. It recognizes threat, stress, and damage, which is what most people think of when they think of the immune system. But it also orchestrates a coordinated healing response amongst your body's 70 trillion cells, half of which are bacterial and viral. And it's doing this for threat neutralization, tissue repair, and adaptation for improved future response. So it is so much more than just identifying a foreign invader and killing it. It is about healing as well. And so we really need to understand how that works so we can support it. At the cellular level, the immune response is orchestrated and executed by the mitochondria. This is so key. This is where we need to look first. And the mitochondria sense threat and damage, coordinate the cellular response, and change shape and mode to usher cells through the stages of healing. So if we want to understand what our lab work is saying, we need to understand what the mitochondria are doing. So let's take a look at how the cells and the tissues in the body are organized. So we're going to look at the levels of organization here. So first, at the smallest level that we're going to look at right now, we've got atoms and ions. So these would include calcium and magnesium and potassium and phosphorus. Basically anything that you would find on the periodic table of elements is an atom, and hopefully not all of those are in your body. And if these come together, then they make a molecule. So a molecule might be something like an amino acid or a lipid. And when molecules come together, they make macromolecules. So an example of that would be DNA or cholesterol or triglycerides. So these are just bigger molecules that are made of these smaller pieces. And then when those come together, they make something called an organelle, which really just means little organ. And so these are little functional units that exist inside of our cells. So an example of that would be the mitochondria, which we're going to spend some time getting to know. It also includes the nucleus and the ribosomes and Golgi apparatus and other things that are a little bit outside of this direct discussion. So a bunch of organelles make up a cell, and a cell is the smallest unit of the body that can be considered alive. So you can have single-celled organisms that can function on their own and be alive. If we get a bunch of cells organized together, then it makes a tissue, which would be like our skin or muscle tissue or nervous tissue. And then if we get a bunch of tissues together, it makes an organ. So that would be like your heart and your brain and your kidneys and your spleen and your liver and your pancreas. So these are all organs that are made up of tissues, which are made up of cells, etc. And then when we have a bunch of organs working together, then we have an organ system like the cardiovascular system or the nervous system, and then a bunch of those together, and we have a person, have a you or me, or an organism, an animal. And so we want to understand that all of these levels of organization are happening at the same time. So in a cell, we can have trillions of reactions happening every second. And that's one level of organization that's happening. And at the same time, you're listening to this and I'm speaking to you, and that's happening, that integration's happening more at the organism level. So we need to understand that we have these different levels and that they need to coordinate with each other in order to have an organized response, including the immune response. And now if we take a look at scales, just to give us an idea, so this is a logarithmic scale, which means that the really small things are very, very small compared to the adult female that we see here. But what's really helpful to just be aware of is that the bacteria and the mitochondria are the same size, and that's actually not a coincidence, which we're going to see in a moment. And then here we can see that we've got our animal cells, and then the human egg, which is also a single cell, is just a bit bigger here. So if we want to understand how and why the immune system functions the way it does, we really need to get a little bit more detail about the mitochondria. So in our body, we have roughly 70 trillion cells, and about half of those are bacterial and viral and fungal, and the other half are human cells, okay? That's about 70 trillion. In terms of mitochondria, we have about 100 quadrillion, which is like a number so big that it doesn't even make sense, right? So just to give you a comparison, that's 1 million times as many stars in the Milky Way. So that's a ton of mitochondria. And if we want to understand how the mitochondria function when we get sick, we do need to understand where they came from and how they evolved. So if we go back to the beginning of the birth of planet Earth, then, and all of these dates are approximate, there's always discussion and nuance in the literature about the estimates, but this is just accurate enough for the purposes of our chat here. So the Earth is roughly 4.5 billions of years old, and the last unicellular common ancestor, known as Luca, lived about 3.9 billion years ago. So this is the organism from which all life on Earth descended. And so a bit more recently from Luca, we get two unicellular, so single-celled organisms. One is the bacteria and the other is the archaea. And these are quite similar, but I think it was discovered in the 1990s that these were actually technically not the same thing. So they're given their separate domains of life. And then what happens is that the archaea and the bacteria find that they each have functions and advantages and aspects that the other could benefit from, and so they join together, and this is how we get what's called a eukaryotic cell. And so a eukaryotic cell is what all animals are made of, and all plants are made of, and all fungi are made of. And so it is the combination of the archaea, this primitive cell, and the bacteria. So here's a little look at our tree of life, and it's just interesting to note that all life came from these bacteria and archaea, that from them we get protists like amoebas, which we can sometimes get infections from, and then from there we get the plant kingdom, but also the fungi kingdom and the animal kingdom. And really it's a little bit of an aside, but it is useful to note that animals are actually really closely related biologically to fungi. So what happened? So why did these two different types of cells come together? Well, something really important happened, which was that when planet Earth was first born and then life on planet Earth happened, there was little to no oxygen in the atmosphere. And then what happened was that the cyanobacteria that was living in the ocean developed a trick to basically take carbon dioxide from the atmosphere and, with the addition of sunlight, make oxygen and some sugars. And so when that happened, the oxygen levels on planet Earth began to rise, and oxygen was really toxic. So most of life on planet Earth at that time became extinct. This was a huge mass extinction. So any life that was going to survive needed to find a way to not find oxygen too toxic, right? Or even, better if it could use oxygen to make energy. And so that's exactly what happened. The archaea found oxygen toxic, but this bacteria, this certain type of bacteria, was able to use it. And so they came together, and the deal that they struck, this cooperation that they struck, was that this bacteria would provide energy by using oxygen and making it less toxic, and in turn the archaea would provide abundant nutrition and an enclosure, right, and safety. So this is just a little bit more looking at what the cyanobacteria is doing. That's taking the water and carbon dioxide, and then it's turning it into oxygen and sugars, and we're getting our first photosynthesis, but we're also giving off lots and lots of oxygen. And so this is just another look at that, but what we can see is that as those levels rose, we have this huge extinction, but we also have the development of eukaryotic cells. And this is really key to understand in terms of how our cells behave when they get infected and stressed. But from there, you can see that the oxygen levels rose, and then we get further evolution, and then we get lots and lots of animals and mammals right after that. We can actually see evidence of these rise in oxygen levels. This is known as the great rusting of the earth. And so you can actually see it in this picture here that this is the oxygen interacting with the iron in the earth. So after we get eukaryotes, which are, about 1.5 billion years ago, then, I'm going to highlight here just some key points in evolution that are relevant to how our immune system works. So we get the development of these multi-celled organisms, these sponges here, that's about 700 million years ago. And then we get kind of more sophisticated multicellular organisms. About 500 million years ago, we get vertebrates, which is an important milestone in our evolution. Then about 250 million years ago, we get mammals. And then a mere 0.3 million years ago, 300,000 years ago, basically just yesterday, we get humans. So this theory of where mitochondria came from is called endosymbiosis, and it was developed by a scientist named Lynn Margulis. And when she first proposed it, it met with a lot of resistance, but it ended up becoming accepted as the predominant theory. And I really like this quote from her: "Life on Earth is more like a verb. It repairs, maintains, recreates, and outdoes itself." So now that we have that background in how cells evolve, now let's take a look at what happens when a cell is stressed. And by stressed, I mean either infected or damaged or cut or too hot or too cold, or even psychological stress coming from higher organization like our brain. When a cell is stressed or injured, it goes through 3 distinct steps to heal, and these are coordinated by the mitochondria. This process is known as the cell danger response. Each step retraces our evolutionary progression and our development, right? So this is key. So if we want to understand what happens when a cell gets infected and what it does to resolve it, then we need to understand how our cells evolve, because they are basically recreating that process in the process of healing. So if you have a health issue, or you have some lab results that you're trying to make sense of, or you have some symptoms and you want to understand why your body is behaving the way it is, you might have a lab test like this that has all these markers, and we have immune markers and white blood cell counts and lymphocytes and iron and all of that. And you want to, you're looking at it to see what's low and what's high. But really, when we look at a lab test, like a blood test or a urine test for any sample, stool, then we're really, it's like we're dipping our cup into a river and taking an ecological sample and measuring what's in there. And what we're measuring is downstream of this process that the mitochondria are orchestrating. And so if we really want to understand why a marker is high or low, then we have to understand this process. And so when a cell is stressed, then it goes through these 3 stages. And in the first stage, it goes back to behaving like a single-celled organism, like an archaea, that didn't to have oxygen. And then it progresses and becomes more like this eukaryotic type of cell. It then becomes, in its identity, a bit more like a multicellular organism, like a sponge. And then as it continues, then it can finally rejoin the network to regain its identity as one of your cells. So really, if we want to understand what disease is, especially chronic disease, complex chronic disease that's so prevalent and ubiquitous in our societies, then one way to look at it is that it's de-evolution. It's evolution backwards, because we have these stressors and we have these multiple layered stressors, and cells and networks of cells are devolving in order to go through this process of healing. So in inflammation, cancer, and chronic disease, mitochondria and cells devolve into more primitive states in order to protect, regrow, repair, and reconnect. So this is by design. This is a feature, not a bug. That's actually how healing works. When this process gets stuck, though, that's when we get chronic disease. So this idea about our individual human development, how you developed from an embryo to to a baby, to a child, to an adult, if you are an adult, was summed up by a scientist known as Ernst Haeckel, and he had this famous quote: "Ontogeny recapitulates phylogeny." And what that means is that the ontogeny, which is the development of an individual organism like you, it repeats the main steps of the evolutionary history of the organism. And so we can see this when we look at the way organisms develop, that they go through these stages that are very reminiscent of much older stages of evolution. And we can see this here when we're looking at how to build a human, that we all start off as a single cell, just like human life started off as a single cell, and then it becomes a group of cells, and then it differentiates into tissues, and then it differentiates into organs, etc., etc. So we see these patterns that are replaying. But what also happens when we are sick, if we have chronic infections, biofilms, injuries, energy issues, any of these things, is that the way we heal also follows this process. How humans evolved from single-celled organisms is mirrored in how each human develops from a single cell, but this is also the process of how we heal. Cells revert to single-celled identity and then go through the stages of development. And this is summed up brilliantly by a fantastic researcher and teacher of mine, Bob Navio. And so he says in one of his articles, "It is no accident that the stages of healing recapitulate the chemical evolution of animal cells. The Precambrian Earth had an atmosphere that was largely devoid of oxygen," which now you know all about. "When capillaries, lymphatics, or glymphatics in the brain are torn by injury or decreased by disease, oxygen delivery and waste removal are impaired. An alternative method of energy production must occur if cells experiencing hypoxia are to survive." So much of what we see on a blood test that's out of range, or all these problems, are really processes that our body is undertaking to try to heal. So it is trying to use these stages of physiology to go through this 3-step process in order to become healthy and whole again. So this makes sense. We think a lot now about how efficient our bodies are at carrying and using oxygen and what our inflammation levels are. But what we need to understand is that if we look at a blood test, for example, and we see that there are markers out of range, these are usually our body's attempt to try to heal itself, that it's gone to this different type of physiology in order to go through the steps of healing. And if we try to use things to just lower those levels and block those numbers, we may get symptomatic relief sometimes, but it almost always comes with side effects and other problems that are created, and it does not facilitate the healing response. It does not help to take us through those stages so that we can become healthy and whole again. So when the body is healing and it goes through these 3 stages, then what happens at the cellular level is a change of identity. So when we are healthy, then let's say a cell on your finger is connected to the greater network, so it knows it's a part of you. But if you cut it, then by design, in order to heal it, it's going to change its identity from being part of your finger cell to being like an independent single cellular organism, so that it can go through these stages of healing that mirror this evolutionary process from cell to oxygen using cell to tissue to vertebrate to mammal and then to human. So the core ideas to understand here, and why this is so important for understanding the immune system, is that as we evolved, we got bigger. So we coordinating from one single cell to 70 trillion cells need to coordinate and understand who is doing what and how to detect and mitigate threat, that we became more complex, but also that our identity changed. And a big part of our immune system is about identity. So understanding what is meant to be there and what is not meant to be there, and to protect ourselves and to wall off or get rid of what shouldn't be there. And so we need to understand that our identity has evolved over time, and that when we have a threat, that our identity or the identity of cells reverts to single cell organism. And And so that this can lead, so if there are too many cells that are doing that, this can lead to problems in correctly identifying who is friend and who is foe. But also that once healing is complete, that it needs to rejoin the network. And we're going to go into much more depth on that. So this is just an overview that if you want to understand how your immune system works and why it does what it does, then we need to understand how we evolved, because the process of healing completely mirrors that process. And in a future video, we're going to go into more depth on the cell danger response and these 3 stages of healing so that we can understand what's going on in our body and how best to support it. Now, if you have a complex chronic illness like mold illness or Lyme disease or chronic fatigue or fibromyalgia or autoimmunity or digestive issues, and you're looking for support, you're motivated and you like to learn and you want to just understand what to do and how to move yourself forward, then you should really consider joining our free group, where it's a solutions and support group over at Synthesis Health Lab. You can ask me any questions that you have. It's completely free to join and get a feel of what it's like there. It's a really friendly group. There may be a wait list because we like to keep it small, but you can feel free to apply. There'll be a link below and you can ask any questions that you have there. And so thanks for watching, and I look forward to seeing you in the next video.